Hello, I'm Professor Reese. As the peanut butter cup, you can pronounce my name as Reese, like the peanut butter cup. However, most people just call me Doc, like the Doc from Back to the Future, all right, Doc. And we're going to do optics. Now, I need to be a little careful with this deck because just a few days ago, the famous bear that had the Trump sticker put on the back, which is very dangerous, by the way. The neighbor that did that is like wow, like crazy, to get that close to a bear. That was on this deck. Like it spent like the morning on this deck, and when I came out on the deck, it surprised me. I stayed in the house. But there's no bear here. Let's go ahead and show you. Yeah, we're good. We're good. We're good. No bear here. Okay, so optics, modern optics, is a great course. Well, all your physics courses are great courses. And this puts another piece to the puzzle for your education in undergraduate physics. And we're going to look at geometrical and physical optics are the two areas of the course. And we'll talk about what those mean in the course when we get started. Even today, we'll be telling you what those mean. So this course has a goal to learn about optics, the goal to learn about geometrical and physical optics. And what are our other goals and say aims and outcomes? Well, one is that mathematics in each of the physics courses helps you, when you apply math, helps you get more proficient in mathematics. So you're going to get here more, let's say, be more of an expert in mathematics, since mathematics is the language of physics. And we're going to start today with the calculus of variations and apply it to optics. A very fascinating connection there. Now, when I taught engineering students for like 7 years, at NC State, I was an adjunct professor of mechanical and aerospace engineering. I discovered that the engineers give homework problems that have lots of calculations to get a number, and that the number is very important. While when I took physics, well, we did a number of calculations, of course, but like the derivation was like the cream of the crop, or like the elegant thing. Do the problem with the general formula. But I found that I'd like you to have the ability to do both. In other words, to appreciate derivations and do the mathematical derivations with symbols, and we'll be doing a lot today with the calculus of variations. But also, we'll be assigning homework problems where the number is very important. Like, what is the index of refraction for, let's say, air or something at a certain temperature, pressure. And that's important to get that number. In engineering, very important. It can be a matter of life or death. For example, if you're designing an elevator or a bridge or a rocket, that you got to have the numbers accurately figured out. And remember the mistake where there was some confusion with the units, like meters versus, say, feet or something similar to that, and we lost millions of dollars on a spacecraft that just like had no person in it. That was good, but still, to lose a spacecraft bouncing off the atmosphere of Mars, that's not good. So in this course, I want you to learn how to do derivations, understand the derivations, but also have an appreciation for engineering, which is very important in engineering, and that is the calculation to get a number. That's very, very important. So I just became more aware of that when I was teaching engineers, all right, that they could do this to a high degree. So they were stronger with numbers, but then physics majors would be stronger with the derivations. And I'd like you to be strong in both areas so that you're prepared to go to the graduate school if you want, or work in a job, for example, where you're very powerful mathematically, and you can apply your training to get precise numbers when you have to get precise numbers, or do calculations when you have to do more, general things like that. And then we also have as a goal interdisciplinary topics. The power of physics reaches out into medical physics. We do the eyeglasses and prescription diopters for eyes. We do camera optics, and we do like microscopes, telescopes, cool stuff there. And that interdisciplinarity, that is because of the power of physics. And also at UNC Asheville, we're a liberal arts school, which we like to do that anyway. Like, so to do applications into camera, or say biology in a medical area, this will be done. And atmospheric science, we're doing a mirage, the second class. We'll be doing rainbows, for example. So that's an overlap with atmospheric sciences. So we'll be doing that too, and I hope that you enjoy the topics we have in our syllabus, a little calendar that shows you by each day where, what the topic is. And for homework, we use a rule that was proposed by a student last semester when I taught a physics major class, and that is you always have the homework due 2 classes after it's assigned. So if you have class A today, say, then it's due at the end of the day for class C. Now, the reason why we just don't say a week is because when we have an exam, then it's more than a week, because when we have an exam, there isn't a class letter. So we go from A to Y in our class. So if you have like homework assignment G, it would be due whenever the calendar says the class is for 2 letters into the future. So what's after G? HI. It'd be due by 11:59, the class of I. Now, what's very important is that you need to figure out how to send me a PDF file, because we're doing this online. Now, the PDF file needs to be less than 25 megabytes, so it can fit, in Gmail, easily. And it needs to be clear, so I can read it. It needs to have good contrast. The letters, to be big enough so I can read it, and the contrast. And also, you need to have the problems in order. So, if you have like 2 assignments, in one assignment, 2 problems, you do problem 1 first and problem second, follows, and you label the problems. And you want to have 1 PDF file, for the whole assignment. So you need to figure out how to do that, and I can help you. You can take like pictures with your camera, your iPhone, for example. And then there's ways to like upload things and even make PDF files online, like for free if you don't have software. Or other folks can scan in. If you have a scanner, you can write your homework out, and always, recopy your homework. Like never like turn in like stuff crossed out and all. That's bad. That's very bad. All right. You want to turn in stuff that's neat. And occasionally, tell me like what you're doing. Like, don't just don't give me a lot of math. Occasionally give me a phrase, all right, so that I can follow. Like if you were doing this for someone else, a fellow student, to understand. Your communication is very, very important. Very, very important. So important that once a retired professor at UNCA, he was chair of the management department, he was a chemist, he said that 99% of all problems in industry is communication. So you really want to communicate, have good reports, good homework assignments, turned in. So that's going to be the first thing to do, to figure out how to get that PDF file that looks good. And then I will be able to make a comment on the PDF file and give you back your homework. All right, let's get started. Here we begin our course in modern optics, and chapter A is going to be on the principle of least time. Introduction first. Here you see a picture of laser light going through a water jet. Most of the light is being reflected internally, following the jet stream, much like a light pipe or like in fiber optics. This picture dates back to the 1980s. You can see the XT computer in the background. And the lady there is Gwen, who was the office assistant for environmental studies which was a program in those days, later became a department. And she's also was also at the time a student. And she's assisting me here with the placement and the experiment. The picture was taken by John Warner, a local photographer who was also at the time my neighbor on Howland Road in Asheville, North Carolina. So this problem can be analyzed by geometrical optics, the total internal reflection. Like if you have a jet stream, for example, like this, say this is a jet of water, then the light comes in here, reflects, total internal reflection, and we're going to look at that later in our course, and that's how light pipe works. Good. And then and try to get it so that you can see the green in the beam. So play around with it. Yo, oh, perfect. Look at that. That is awesome. Geometrical optics. So what is with this geometrical optics? Well, you got three areas of optics. You have your geometrical optics, light travels in straight lines, and then you have physical optics, light as waves, and then quantum optics, light as particles. So for the first level, geometrical optics, light can be taken to travel in straight lines. In the second case, physical optics, light travels as waves, has crests and valleys, crests and troughs. And in quantum optics, the third level, light acts like a particle. So our course is, the description is a study of geometrical and physical optics, prerequisite physics 222, which is calculus base physics intro sequence. That's the second one of the 221, 222. And we're offered the course at even years in the fall. Now, I like physics, how over the years, when new physics is discovered, often it replaces the other physics. Well, it incorporates it. Like when the first physics is good, like Newton's laws, then when Einstein's laws come along, Einstein's laws incorporate Newton. So in Einstein's equations, you have the speed of light, lowercase c, showing up a lot, and then you have your velocity divided by c appearing a lot. And in those equations, if your speed v is less, very much less than c, so that this is very much less than 1, then you recover Newton's laws. Now that is really neat. So you get Newton's laws, and you can see here in a quick little summary, if I have here a speed, laws of physics, and here you have, say, size, and if this is small down here, we're going to make the large one on the left, and this is slow, and this is fast, then if you look at these regions, this is a classical mechanics, that's Newtonian physics, large and slow. Large if you can touch it. Apple you can touch the earth, they're large. And then here if you're fast, that's Einstein, relativistic mechanics. And then here this is quantum mechanics if it's small, and this is relativistic quantum mechanics. So what we're saying is that this law of Einstein can recover Newton's laws if the speed that you're traveling, if you slow down and you don't go so fast. And here, if little molecules and atoms become replaced by bigger, like apples and oranges, then quantum mechanics becomes Newton's laws recovered. And this is then the law of the super, fast and small. That would incorporate all these laws. So when I look at the geometrical optics, the physical, the quantum, I remember the great poet Wordsworth in Tintern Abbey, who said that there were 3 levels of appreciating nature. You can appreciate nature as a doe bounding, like in the forest. I like to think of the first one as like the way a kid would run around, roll in the grass with a puppy, or play hide and go seek. And then 2, when you get older, you enjoy the sublime beauty of nature, the breathtaking beauty of nature. Say that's like you're young adult, like a teenager or something. And then when you're mature, say adult, you look at nature as your moral guardian and teacher. So if you have a question in life, you walk into the woods for 2 hours and get your answer. My point here is that the mature person can still step back and act like the teenager and appreciate the sublime beauty of nature, and also can roll around in the grass with a younger sister or a cousin and with a puppy dog and play hide and go seek. So the mature person doesn't eliminate the earlier behavior, it incorporates it. And that's what the physics does. The quantum optics incorporates the physical optics, and the physical optics incorporates geometrical optics. So let's look at here a nice demonstration of that in our next section, A1, which is light travels in straight lines. Now that's geometrical optics. And that dates back to Euclid, of Euclidean geometry fame, many, many years ago. And Euclid, considered the founder of geometry, Euclidean geometry, and this is geometry based on flat surfaces. Later mathematicians extended that with Riemannian geometry, curved surfaces, and Einstein in general relativity uses curved space-time. But in flat spaces, then light travels in, or the distance between A and B is a straight line, closest, the shortest distance, and light travels in straight lines. And it's appropriate that we call this area of optics geometrical optics after the inventor. The inventor, Euclid, the inventor of geometry, is basically geometry. So that's the point there. It's like a geometry thing. Here's an example of something I show in class where students take laser beams, handheld laser beams, pointers, and they shine them at me. I then take 2 erasers and make some dust, chalk particles, like dust in the air. And the little chalk particles then allow the light to reflect and scatter, reflect off the chalk. And you can see that the path of the light is a straight line. Very, very impressive demonstration. Isn't that nice? Okay, so we're ready to do the experiment. We got some erasers here that has some chalk on. I will make some dust. Now we're going to go dark. Yeah, go ahead. Yeah, get a little closer with your arm. Yeah, go ahead and shine. Everyone see that? Isn't it cool? Now check this out. Yeah, that's good. Isn't that nice? That green one's amazing. The blue one's not as bright. We're not as sensitive to light in the blue. I like it. You cross them over. That's nice. That's good. There you go. Hit me. And we're going to look at the beautiful mathematics of the calculus of variations, which you probably encountered first in a calculus class. But it's nice to see the calculus of variations in different ways, approached by a physicist or a mathematician. And I'm going to show you, with the calculus of variations, proof that the shortest distance between 2 points is a straight line. And even though it's a simple result, the training you get in mathematics to go through the steps is very, very important. And the approach I'm going to take, use some notation from Richard Feynman, who did a nice analysis for Caltech students back in the early 1960s, and I'm going to do it in a style using some of his notation and his methods. So here's how we start. We have a Cartesian coordinate system. We have X and Y. And we have a point A where we're going to start and a point B where we're going to end up. Now we know the answer is the straight line, is the ideal path, because we're looking for the shortest distance. And let's call that Y bar of X. But you can have a general function that is a path that's not the ideal. And in this case, this is some general y of x. And if you look at some arbitrary point x, you could go up to find the ideal value for the y. It's y, this is y bar. And then if you go up the rest of the way, we'll call that eta, the piece. So the general function y consists of the y bar height and then the eta. So I can write this as y of x is equal to y bar of x, that's that first height, plus eta of x. Then we know from calculus that we can calculate the arc length by looking at some arbitrary curve and looking at a nice little right triangle. And when this triangle is small, this arc length, delta S, will lie along that hypotenuse. Here's your delta x and here's your delta y. And you use the Pythagorean theorem that delta S is going to be given by the square root of delta x squared plus delta y squared. So then what we can do is we can factor out, like they do in calculus classes, they can factor out the delta x. And if you do that, you get 1 plus delta y over delta x squared delta x. Let's just check that. If the delta x goes inside the square root sign, it goes in as a delta x squared. And then that means it'll kill this delta x squared in the denominator to get you just delta y squared. And when delta x squared goes in there and hits that 1, you're going to get a delta x squared. So these are the same, the arc length, the differential arc length. Now this, say in the limit, as delta x goes to 0, this is then dy dx. This is your derivative, often just given as a y prime. So that means if we looked at the ds and say integrate it from a to b, that's going to get you the arc length, the total arc length, which you want to be minimized. So if we do this, we're going to have here the integral a to b with this square root thing. All right, there's a square root, and that's going to be 1 plus, and then we're going to have here the derivative squared, and we have dx. So that's the integral that we want to minimize. Now you are familiar with max-min problems where you have some function, say f of x, and you want to minimize or maximize it, find the extremum. You take df dx and set equals 0, and then you find like a max, or you find like, a max or a min. But see, we're doing something more complicated here. We're finding a function. So this is the concept of a functional, and you have a functional to find the best function that gets the job done, while in this max-min problem, you use a function to find like x, a specific x that gets you your max or your min. I hear there's like 2 of them there, so x1, let's say x2. But if you're looking at, say, something like functional setup and then find a function, that's the calculus of variations, all right? So what we're going to do at this point is replace the y prime, well, first the y, just replace the y here. See this here, we're going to use this, and then do the prime on there. So that would be y prime of x, y prime as the derivative, and it's a function of x. And that's going to be here, we're going to have then the derivative of the bar function, and then the derivative of the eta function, since the derivative of the y is sum of the 2 derivatives. And so that's going to go down in here. But we got to square this thing. So if we square this thing, we're going to get here y bar prime squared plus, then there's going to be 2 y bar prime eta prime, the cross term, and then plus eta prime squared. Now, when you get close to this desired solution, you're going to have eta being small. So when eta gets small, as we get to the correct solution, here is a quantity that's small that's squared. Well, see, if you have a small quantity, like say like 1 over 10, then if you square it, you get like 1 over 100. Well, that's like extra small. So we're going to neglect this. And as we get closer and closer to the desired result, the eta is going to approach 0. So when we have this set up, we're going to plug this into the equation down here. And when we do that, let's see if we can keep track of all the stuff that we have. The first thing we have is a 1. That's this one here. And then the next thing we have is this piece is going to be second. So we're going to put that inside. That's the y bar prime squared. And then the next piece is this one. And that's going to go in, because that you're taking a square root of, see, this thing here is inside a square root sign. So that's going to be then 2 y bar prime eta prime. And then there's the dx. So that's the setup. Now we can do another trick. See, this is very nice, even though the answer is, you know the answer. You're learning so much physics and mathematics here, because now we're going to do the Taylor series expansion, which is so commonly done in physics, where what you have is you have a small piece and a bigger piece. And this is going to be the small piece here. So watch this trick. We're going to take the S and we're going to pull out the square root of 1 plus y bar prime squared. So if I pull that out, then I get where it was, I'm going to get a 1. And then over here, I have to divide by it. So this is going to be divided by the 1 plus y bar prime, that quantity squared, dx. All right, so let's look at this to make sure that we have gotten everything correct. If this goes inside the radical sign, since this is a radical sign already, and that's a radical sign already, you just put that in there for where the 1 is. So it's this times 1, and that's going to get you this part. Then when this hits the second part, it's going to cancel the denominator, and you're going to get then just the 2 y bar prime eta prime. So that's correct. But see, now this eta is small, so that means I can look at this as having a 1 plus a small quantity with a square root sign, and that would be 1 plus epsilon to the 1/2 power. And it's nice to know that 1 plus a small quantity to the nth power is approximately 1 plus n times epsilon. You know, there's other stuff there, but this is basically if the epsilon is small, because see, when you do your power series, you get an epsilon squared and an epsilon cubed, you know, in those cases. But then if the square is 1 over 100, and then the cube is 1 over 1,000, and you know, the fourth power is 1 over 10,000, it's like you can neglect all those terms, and this is a good approximation. So that means this is 1 plus epsilon over 2. And here, when I look at the epsilon, let's go ahead and write the epsilon is the 2 y bar prime eta prime over 1 plus y bar prime squared. So when you look at the epsilon and divide by 2, that 2 will go away, and you'll just have the rest of the stuff there. So this arc length total, let's go ahead and do that, from A to B, we're going to have this first part here, the 1 plus the y bar prime squared. And then now this square root sign is gone. You're going to have a 1. That's this one here. Then you're going to have the epsilon over 2, which is everything here without that 2. So that's y bar prime eta prime over 1 plus y bar prime squared, and then dx. All right. So this is very, very elegant, where we can write down now that this is the part that's going to get me the correct answer, and this is the error term. See, because see, y bar, that's the correct answer, that's the straight line. So I can write this as having the correct answer, the S bar version, plus this other version is some variation, say, or a deviation, some variation of the arc length. And I want this to be 0. When I make that 0, I'm going to find the function. That's the logic. Well, what is the variation of the arc length? What is the second piece? Well, you got to take this and hit it with that. That means you're going to get y. You're going to have also an integral. You have your integral. You have your a to b, and you're going to have y bar prime eta prime. But now that's going to be down in here a square root. You're going to have a square root, since this is a square root, and you have 1 over the same thing without a square root, so that's going to make it a square root. So then that's here dx. So this has to be equal to 0. If we can find the function y bar that makes that work, we're going to be in good shape. Now the trick here is to notice that the eta prime is the derivative of eta with respect to x, and the etas themselves, these are the deviations, and they're arbitrary because I can make that y in general, any kind of curve I want. And that means these etas are going to vary, except that you have to start at a and you have to end at b. So the value where x is equal to x to a, that has to be 0. You have to start here. There's no error there. And then if you look at eta, say at point B, that has to be 0. But everywhere else can be anything. So the trick is to get the dx off of that thing so that the arbitrariness can be out in the open. And to lift that derivative off of there, we use the integration by parts. Or you can think of integration by parts as a variation here of the product rule. So if I have here y bar prime, say eta, and then I have over here 1 plus y bar prime, that's squared. If I look at this, I'm going to get one of the pieces is going to be what I have there. I'm going to take the derivative of the first one, all right? And the derivative of the first one is all this stuff. All right, like this. And that's going to multiply then to eta. And then we're going to have all the first stuff, which is the y bar prime. And that's going to be over 1 plus y bar prime squared. And that's the first one, and the second is going to be this eta. Okay, so that's not there. Sorry about that. So here, what we're looking at okay, so let's look at this again. The first function here is going to be all this stuff except the eta. So I took the derivative of all that and had the eta on the outside. All right. And then the derivative of the eta comes next. So you can think of this as like having, d dx of an f and a g. And you're going to have then df dx times g plus f times dg dx. And the f is the y bar prime over the square root of 1 plus y bar prime squared. And the g is the eta. So the derivative of everything but the eta, and then times eta, and then here all the first stuff, and then the derivative with respect to x of the eta. So this is what we have in there. So we're going to replace it with two integrals. And you might say, well, isn't that bad? Well, actually it's not. I'll show you why here, because this is a perfect derivative, and this one here is perfect derivative, and when you take the integral, you'll just lift it. So let's go ahead and write out the steps. Here is d dx y bar prime eta over the square root of 1 plus y bar prime squared. All right, that's the first term. And now we're going to look at the second term. All right, let's go ahead and put the dx on there like that. And then the second term is going to actually be a negative, because this is what we have. So we have to replace it with the left side minus this part. So if we do that, we then get d dx y bar prime over the square root of 1 plus y bar prime squared. And that's going to have an 8 on the outside and dx. This has to be 0. Now this one, see, the integral of a derivative, that just lifts this. And if you lift this off like this, and then evaluated a and b, remember that the eta at the endpoint's 0. There is no error there. So that means this is going to be 0. And here, since these are arbitrary, that means that everything here has to be 0 so that the equation is true all the time, because you can't count on eta for some path conspiring to get a 0 integral. So you can then change it to some other path and it won't be 0. So this has to be 0. But that's a derivative. So if a derivative of something is 0, that means that this inside the derivative must be equal to a constant. But here you just have y bar primes everywhere. So that means the y bar prime has to be equal to a constant. And that means dy bar dx is a constant, which means y bar has to be equal to mx plus b, which is our straight line. And since we found the correct answer now, the y bar and the y are the same, since the eta is now 0 everywhere for the correct case. So that means y is mx plus b. We can just replace the y bar with the y, and we have our answer. Very, very elegant. Let's look at what we have done here. We have taken the arc length from A to B, where we have some arbitrary y, and we did a minimization problem to find what that y is. Now in calculus class, where you have a function, f of x, and you take a derivative and set it equal to 0, you get the max or the min. And notice that the function at this point, the variation of the function at the top or the bottom here, is 0. So if you do a little displacement left or right, you get 0 because it's flat. So it's not changing in that infinitesimal place. Here you have a function of a function. So we call that a functional. And when we do the minimization, we get a function. So here, when we did the max-min, the derivative, we got a point, a value x. The answer is x1 or x2. Here, when you start with the functional and you do the minimization, the answer is a function. And the function is given by the formula that we have down here. What I would like to do is change the variables so that we're looking at x and t like in mechanics, and then you have here your derivative is your velocity. So in that case, if we look at the equations that we have from before, we have from a to b, we had the square root 1 plus y prime squared dx, all right? And the answer that we got when we worked that out, the answer that we got here was given by this equation, d dx y bar prime square root of 1 plus y bar prime squared. That derivative has to be equal to 0. That's what we have down in here, just copied. Now, to make the transfer of the variable, what we need to do is replace the x by t. So we're going to look at here s going from a to b. And what I'm going to do here, the x is going to become, the old x is going to become the new t, the old y is going to become the x. And the old y prime is going to be the derivative of x with respect to time, which we'll call x dot. So then this is a 1 plus, and then the y prime is an x dot. So this is an x dot, and that's going to be s squared. And you have then dt. Then this here is a d dt. But notice that what's inside here is the derivative of this with respect to y prime. So that would, here that would take 1 over the square root thing, and then the derivative of the inside is 2y prime. So if you look at that, if you look at this here, 1 plus y prime squared, and do a derivative, the 1/2 comes down, and you get the 1 plus y prime squared to the negative 1/2, and then you have the derivative of the inside 2y prime. So the 2 cancels that 1/2, and then that is what you got on the inside here. So this is here the derivative of, and let's call this integrand here, we can just call that L. All right, so then dl dy prime, this is equal to 0. This is actually an x in terms of not doing the substitution yet, just to have what we have in the old case. But now we're going to do the substitution, and that's d dt, and that would be dl dx dot equal to 0. So when the L is only a function of x dot, then that's what you get. But suppose you had a more general case where, say, the integrand going from a to b is some function of x dot, but also a function of x. And said you want to minimize this. And this is going to be a new a new thing now. It's not going to be this one when I apply it to mechanics. So let's look at this. If you want to take the variation, and this is the idea of the variation here, then you can think of this as taking a variation of the L. And now watch this. Watch me derive this in like just like 2 lines. And this is my inspiration. You know, when Feynman, a theoretical physicist, he would often derive things very, very quickly. Right? Very profound derivation. So here, the variation would be, well, it would be the partial of L with respect to, say, x dot, and then there'd be a variation in x dot, and then there'd be the partial of L with respect to x, and the variation in x. All right, and dt has to be 0. Now, if you look, before we only had this term. And when we had this term, we had to pop off. See, we had this variation on the dx dt, and we wanted to pop off that derivative. And that's how we got this on the outside. So if we do the same thing here with the t, then this is going to be d dt, and that's going to be the partial of L with respect to x dot. That's going to be this first term. But you know, this second term, this second term. Oh, by the way, excuse me. There's a minus sign when you pop over like that. You get a minus sign. Remember, we use the integration by parts. But then look at this. When you do this to free up the variation in the x, here's already freed up. You're already freed up. So if you look at this situation where you pull this out, like we had before. We had something there times a variation of x, you know, dt equals 0. All this had to be 0. And before we just had the one term. This is one term. Now we have 2. So we get the result here that these have to be equal. In other words, d dt and the partial of L with respect to x dot has to equal the partial of L with respect to x. And it's the Euler-Lagrange equation. Now watch this. If the Lagrangian is equal to the kinetic energy, this is 1/2 mv squared, minus the potential energy. Wow. Because you're used to, in introductory classes, doing the total energy where you put a plus sign, like this, where this is the kinetic energy plus the potential energy. But notice this. With the minus sign, look at what you get here. The partial of L with respect to x dot, the 2 comes down to simply mv, which is the momentum. And then if you take the derivative on this thing, you get the derivative of the momentum with respect to time. And if the mass is constant, no rocket problems, then you have the derivative of v with respect to time. You have ma, mass times acceleration. But what is this on the other side of the equation? Because you have ma on this side, and what is this? Well, if you take the partial of L with respect to x, you go in there and take the partial of this v thing, because that's where the x dependency is. So this is to be minus, and it could be now no longer a partial because it's just x. It's just one derivative there, the regular derivative. And that's equal to the force. When you have a conservative force, that's your famous equation where your potential, the derivative of the potential, you know, with a minus sign, you get the force. You know, like if you have the potential is like 1/2 kx squared for a spring, then negative dv dx is negative kx. That's the force. That's Hooke's law. Or if you have mg x, where x is the height, and take the derivative of the minus sign, you get then minus mg. That's like the force of gravity pulling you down. So that's the force. This is the force. This is ma. You got F equals ma. So in other words, when you go from point A to point B and minimize this integral with the Lagrangian, and that's called the action, when you minimize the action, you get a path that obeys F equals ma. It's like the path it's going to take obeys Newton's law. So this is a very, very sophisticated application in mechanics, and you can see it, the tools that we did in optics, you can see how it's related. Now, we're not going to worry about this in our course. This is an extra bonus. You're going to study that in detail in your mechanics class, and that's the proper place to, to work with that. I just wanted to make the connection to show you how optics and mechanics both have minimization principles. The principle of least action for mechanics, and in optics, the principle of least time for the path. And that is just a wonderful connection and deep, deep theoretical physics to see all these relationships. So you can put this aside for your mechanics course, and when you see it there, it'll be neat to have a reinforcement of this basic idea. So you're going to get this in another course, but I just wanted to show you that what we're doing is very, very powerful in physics. And so in mechanics, if you take the Lagrangian, which is the kinetic energy minus the potential energy, and that gets minimized when you go from point A to point B. So all the paths from point A to point B, the one that's going to get realized is the one where F equals ma, the one that obeys the laws of Newton, the laws of physics. Okay, let's look at here one more thing for today, and that's the next part where we're looking at here the application optics, the principle of least time. Now this goes back many, many years to the Greeks. The principle of least time goes back to the Greeks, a Greek mathematician by the name of Hieron of Alexandria. Now, Alexandria, he was born in Egypt, but he's a Greek mathematician, and inventor, and he promoted the idea that light takes the shortest path between 2 points, which we would look at as light taking the least time. Now, this is way, way back in the old days. I mean, we're looking at like around 2,000 years ago for this. And we had to wait until Fermat, and when Pierre de Fermat came along, he gave us the principle of least time, where you have two media, like glass, say, and air. While think of Hieron of Alexandria as dealing with going from point A to point B in air, or in one medium. But before we go on, I have to tell you about this great story of Pierre de Fermat. The famous equation, Fermat's last theorem. Now this guy is living in the 1600s, so we're, say, around 1650. He's saying that if you have integers, positive integers for everything, that this is only going to work, your positive integers, 1, 2, 3, 4, like that. This is only going to work if n is equal to 1. You can find solutions. So if you have a to 1 plus b to 1 equals c to 1, you can find solutions. For example, 3 plus 5 equals 8. So a is 3, b is 5, and c is 8. And to the first power, that's simply saying 3 plus 5 is 8. You could also find solutions if n is equal to 2. That's the famous Pythagorean theorem, a squared plus b squared equals c squared, and the real cool example is the 3, 4, and the 5. So if you have 3 squared plus 4 squared, that's 5 squared, and that works. 9 plus 16 equals 25. And I'm very fond of a figure I saw in grade school where they had a 3, 4, and a 5, and they went ahead and they did this. This is kind of cool. And I could see there's 9 things there. Then it came down here, 1, 2, 3, 4, 1, 2. And there was like 16 things down there. And then he came up here, and he says 1, 2, 3. So there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there's like 25 things there. That's kind of cool to see that. So he's saying if n is equal to 3, you'll find no solutions. If n is equal to 4, you'll find no solutions. If n is equal to 100, you'll find those solutions, and on up to infinity. And Fermat wrote, I have discovered a truly remarkable proof of this theorem, which this margin is too small to contain. So he writes this in the margin. Well, this is around 1650. By 1750, no one has proved it. By 1850, no one has proved it. By 1950, no one has proved it. And in 1990, it finally gets proven, all right? Using mathematics that was not discovered until after the time of Fermat. So now the question is, did Fermat make an error in his proof, but came up with the right conclusion? Or was Fermat's intuition so great that he really didn't have a full proof, but his intuition led him to make the claim? Anyway, it's a cool story, something that took over 300 years to verify that Fermat's last theorem is correct. All right, so let's apply Fermat's principle of least time, and we're going to do this. Say if you go here from, say, air to glass, light travels slower in glass and faster in the air, and then if the light should hit the boundary and you make a normal is perpendicular, you get some here, normal. It's always good to draw that normal like this. What's the light going to do? Well, I like to make this a problem where there's a lifeguard and you have sand where the lifeguard can run fast, and then here you have water where the lifeguard has to swim but slower, and there's a person here that's drowning, and this person, help, save me. So you got to get to that person as fast as possible, the principle of least time. So here, if you were to go in a straight line, the shortest distance, that won't work because you're going to be swimming too much. So what you do is actually you run more and then you bend and turn. So in other words, you run more on the sand and then you turn and swim a shorter distance, all right? And that's going to be the shorter amount of time. And that's called the law of refraction, which we can derive. And we'll do that in another class, the law of refraction. Okay, this here, last thing to show you is the ants. The ants have figured out how to do it. In other words, the ants have to go from the left upper region to the lower right region to get to the food. So they are traveling pretty much along a straight line that then there's a bend toward the normal. They bend downward, just like we did in our notes. And by bending downward, they then get to the food in the shortest possible time. That green region is either grass or maybe some mesh over some ground where the ants have trouble, traveling fast, but they can travel fast in a white region, like pavement, say. So they're basically showing the law of refraction, which is also the principle of least time.